Number 1. The Mantle, beneath the ocean floor. The closest place no human has ever reached is not far away at all. It is straight down, beneath the floor of the sea. In 1909, a Croatian seismologist named Andrije Mohorovičić noticed something strange in earthquake waves. They suddenly sped up at a certain depth. He had found the boundary between Earth's crust and its mantle. Today we call it the Mohorovičić discontinuity, or simply the MOHO. It is a border, and we have never crossed it. Under the continents, the MOHO sits 30 to 50 kilometers down. But under the ocean, the crust is thin. The MOHO lies only 5 to 7 kilometers below the seafloor. That is why the ocean became the obvious place to try. Reach the deep sea, drill a few kilometers, and you could touch the mantle itself. In 1961, that is exactly what a group of scientists set out to do. They called it Project Molloy. The first attempt drilled off Guadalupe Island near Mexico from a ship called the Cus 1. In 3,558 meters of water, the crew bored 183 meters into the seabed. For its time, that was astonishing. The novelist John Steinbeck watched it happen and wrote about it for Life magazine. The world was paying attention, but the dream collapsed. Costs spiraled past $125 million, and in 1966 Congress canceled the project. The mantle stayed out of reach. The deepest hole ever drilled into oceanic crust came later. It is called Hole 1256D, and it reached about 1,507 meters into the dark gabbro, still far short of the MOHO. On land, the Soviet Kola super deep borehole punched down 12,262 meters, yet it too never touched the mantle. The Japanese drillship Chikyu was built for this very goal, and in 2019 set a scientific record of around 3,262 meters below the seabed. Mantle rock is peridotite, dense and rich in the mineral olivine. We have never sampled it in place. Every piece we study washed up secondhand, lifted by tectonics or exposed at fractures. Reaching it would cost around $1 billion in years of drilling through temperatures above 250 degrees. Here's the paradox to hold on to. We walked on the moon before we ever reached the rock a few kilometers beneath the waves. Number 2. The seafloor beneath Point Nemo. If the first place is unreachable because it is buried, the second is unreachable because it is alone. Point Nemo is the most remote spot in any ocean, the place farthest from any land on Earth. It was not found by a ship, it was calculated. In 1992, a survey engineer named Hervoyer Lucatella used a computer program to find the single point in the sea equidistant from the nearest coastlines. He named it Nemo, Latin for no one, a nod to Jules Verne's Captain Nemo. The point sits in the South Pacific near 49 degrees south and 123 degrees west. The three closest pieces of land are each about 2,688 kilometers away. One is Ducie Island near Pitcairn. Another is a tiny islet near Easter Island. The third lies off the coast of Antarctica. They are so distant that the nearest humans are often not on a ship at all. They are astronauts, passing overhead on the International Space Station, 400 kilometers up. Beneath this lonely coordinate, the water is roughly 4,000 meters deep. The surface above belongs to the South Pacific Gyre, one of the emptiest stretches of ocean on the planet. Scientists call it an oceanic desert. The water carries almost no nutrients, almost no life near the top, and it is some of the clearest seawater ever measured. Nothing marks the spot. There is no island, no reef, no current you could see. It is a point on a map and an emptiness in person. This region has another name, the Spacecraft Cemetery. Because it is so far from anyone, space agencies steer their dead satellites and stations here to burn and sink. The Russian space station Mir came down near here in 2001. More than 263 spacecraft have been deliberately dropped into the broader zone since 1971. The International Space Station is expected to follow around 2030. And yet the seabed directly below has never been visited by a crewed submersible. There is no scientific prize, no resource, no reason that has justified the journey. The remoteness means that if anything went wrong, rescue would be days away. When drilling expeditions sampled this gyre's sediments, they found microbes surviving on almost no energy, some cells perhaps millions of years old. Life clings on, even here. But no person has ever stood on that floor. From the loneliest place, we go to the hottest. Number 3. The magma chamber of the Havre Seamount. Some places are unreachable not because of distance or depth, but because they would destroy anything that entered. The magma chamber of an underwater volcano is one of them. Consider the Havre Seamount, a submarine volcano in the Kermadec Arc, northeast of New Zealand. Its summit hides 650 to 900 meters beneath the surface. For years, almost nobody knew it was dangerous. Then, in July of 2012, it erupted. The blast was the largest deep ocean eruption of its kind ever recorded, and the first sign came from space. Satellites spotted a vast raft of floating pumice on the sea surface. It started at around 400 square kilometers and spread to cover more than 20,000. An airline passenger photographed the strange gray island of stone from her window. Only later did scientists piece together what had happened far below. In 2015, a team led by Rebecca Carey and Adam Soul went to investigate using the robotic vehicles Sentry and Jason. They mapped the seabed down to the centimeter. They found that the eruption had burst from about 14 separate vents along the rim of the caldera at depths between 900 and 1,220 meters. Roughly 75% of the erupted material had simply floated away in that pumice raft, making the event maddeningly hard to reconstruct. The magma itself was rhyolite, thick and rich in silica, the kind that usually drives violent eruptions. Beneath the caldera lies the chamber that fed it, a reservoir of molten and half-molten rock. Its temperature sits somewhere between 700 and 900 degrees. There is no submarine, no robot, no instrument that can enter molten stone and survive. The chamber is a place defined entirely by lethal heat. The Havre eruption rewrote a comfortable assumption. Scientists had thought the crushing pressure of deep water would smother explosive volcanism. It did not. The deep can still fragment magma and loft stone to the surface. Yet no one has ever directly observed an active submarine magma chamber. We image their rough shapes with seismic waves like a blurry medical scan, but the inside stays hidden. Pumice from eruptions like this even carries living organisms across oceans, rafting coral and barnacles to new shores. Heat keeps us out here. But there is a place where heat does something even stranger to water itself. Number 4. The supercritical water of the Beebe vent field. At the bottom of the Cayman Trough in the Caribbean lie the deepest hydrothermal vents known on Earth. They are called the Beebe vent field, almost 5,000 meters down. They were discovered in 2010 by a British team led by Doug Connolly and John Copley, using an autonomous vehicle and a remotely operated one lowered from a research ship. The field is named after William Beebe, the naturalist who descended into the deep in a steel sphere back in the 1930s. What makes these vents extraordinary is the state of the water leaving them. The fluid pours out at around 401 degrees. At nearly 5,000 meters, the pressure is about 500 times the pressure at the surface. Combine that heat and that pressure, and the water crosses a threshold. It becomes supercritical. It is no longer quite liquid and no longer quite gas. It flows with the freedom of a vapor, but carries the density of a liquid, and it dissolves metals and minerals in ways ordinary seawater never could. These are black smokers. The superheated fluid carries dissolved metals, and the moment it hits the near-freezing seawater around it, those metals precipitate into dark clouds. At Beebe, the chimneys are unusually rich in copper. The plume of the hot water rises more than 1,000 meters above the seafloor before it spreads. Swarms of pale shrimp of the genus Rimicaris crowd the chimneys, and remarkably they resemble shrimp found at vents across the Atlantic, hinting at hidden highways of life in the deep. No human submersible can sit in that vent mouth. No standard instrument can either. The supercritical zone would cook and corrode anything placed inside it. Everything we know comes from robotic arms reaching in carefully at the cooler edges of the plume. The very heart of the vent stays untouched. These places matter far beyond their strangeness. The chemistry of hot, mineral-rich water meeting cold sea is one of the leading theories for where life on Earth began. That same chemistry is now a model for what might exist on the icy ocean moons of Jupiter and Saturn, worlds like Europa and Enceladus. The Beebe field showed that even the slowest spreading, deepest ridges can host furious activity. From the hottest water in the sea, we traveled to the coldest deep no one had reached. Number 5, the Molloy Deep. Almost everyone has heard of the Challenger Deep, the deepest point of the Pacific. far fewer know its frozen northern cousin. The Molloy Deep is the deepest point of the entire Arctic Ocean, plunging to about 5,550 meters. It hides in the Fram Strait, the stretch of water between Greenland and the islands of Svalbard. It is named after the American geophysicist Arthur Edward Molloy. The deep sites inside a steep depression linked to the Molloy Transform Fault, where two tectonic plates grind slowly past one another. This is not a long trench like those in the Pacific. It is a localized hole, carved by the ultra-slow pulling apart of the Eurasian and North American plates. The Fram Strait that holds it is the only deep gateway between the Arctic Ocean and the rest of the world's seas, which makes it quietly important to the entire planet. For almost all of human history, no one reached the bottom of the Molloy Deep. It was simply too remote, too cold, and too often locked under drifting sea ice. Only in 2019 did the explorer Victor Vescovo descend to its floor in his submersible as part of an expedition to reach the deepest point of every ocean. Until that moment, it remained one of the last great deeps no human had ever touched. The conditions explain the silence. The water at the bottom hovers near or below 0 degrees. The pressure is roughly 550 times that at the surface. And for much of the year, sea ice covers the strait, making it dangerous and expensive to bring a ship and a submersible into position. Research icebreakers like the German vessel Polar Stern have refined its depth with sonar, but visits are vanishingly rare. This deep is more than a record. The Fram Strait is a place where cold, dense Arctic water forms and sinks, feeding the great conveyor of ocean currents that moves heat around the globe. Sediment cores pulled from the region store the history of Arctic sea ice and ancient climate layer by layer. As the Arctic warms and its ice retreats, the oceanography of this gateway is changing in ways we barely understand. The Arctic's deepest point remains one of the least studied places on Earth. Now we leave a single hole for an abyss the size of a continent. Number 6. The Clarion-Clipperton Zone Nodule Fields. In the Central Pacific between Hawaii and Mexico lies a plain so vast it is hard to picture. The Clarion-Clipperton Zone covers somewhere between 4.5 and 6 million square kilometers, an area comparable to the entire continental United States. It is bounded by two great fractures in the seafloor, the Clarion Fracture Zone to the north and the Clipperton Fracture Zone to the south. Across all of it, the water runs 4,000 to 5,500 meters deep in permanent darkness. The floor of this plain is carpeted with strange objects. They are polymetallic nodules, lumps roughly the size of potatoes scattered like cobblestones across the mud. Each one is rich in manganese, nickel, copper, cobalt, and rare earth elements, and each one grew with almost unbelievable slowness, adding only millimeters of material every million years. Some of these nodules are older than the dinosaurs. That mineral wealth is why this remote plain is now at the center of a global argument. The zone may hold more nickel, cobalt, and manganese than all the reserves on land combined. An organization called the International Seabed Authority, based in Jamaica, governs this seabed, which lies beyond any single nation's control. By the middle of the 2020s, it had granted more than a dozen exploration contracts to companies in countries eager to mine. 9 areas have been set aside, untouched, to protect whatever lives there. And life does live there, far more than anyone expected. Surveys led by the Natural History Museum in London suggest the zone may hold thousands of species, the great majority of them new to science. One study estimated more than 5,000 kinds of animal, with up to 90% never described. There are sea cucumbers nicknamed gummy squirrels, sponges, and corals that grow only on the hard nodules. In 2024, researchers even reported evidence of dark oxygen seemingly produced at the seafloor by the nodules themselves, a claim still fiercely debated. Despite all this interest, only a tiny fraction of the zone has ever been directly seen by cameras or sampled by hand. It is too large, too deep, and too far from land, requiring days of sailing just to arrive. Robots have crawled across small patches, a few crude descents have glimpsed it. But as a place, it remains almost entirely unvisited, even as machines prepare to harvest it. From a plain too vast to explore, we go to a trench too remote to reach. Number 7. The Romanche Trench. Near the equator, in the middle of the Atlantic, the seafloor splits open into one of the deepest gashes in the entire ocean. This is the Romanche Trench, dropping to about 7,760 meters. It is the deepest point of the equatorial Atlantic, and it takes its name from a French Navy ship, the Romanche, which first sounded these waters back in 1883. Despite the name, this is not a trench in the usual sense. It is a fracture zone, an enormous tear where the mid-Atlantic ridge is offset sideways by roughly 900 kilometers. The ridge is the underwater mountain range running down the center of the Atlantic, and the Romanche fracture zone slices clean across it. This creates a deep channel, and that channel does something vital. It lets the coldest, densest water on Earth flow through. That water is Antarctic bottom water, formed near the South Pole, sinking and creeping along the seafloor. The Romanche Gap is one of the few passages deep enough to let it cross from the western Atlantic into the eastern basins. As it pours through, it mixes violently, and that mixing helps drive the slow global circulation that regulates the planet's heat. The trench is, in effect, a deep valve in the ocean's plumbing. Because it formed by plates sliding past one another, rather than one diving beneath the other, the walls of the Romanche expose deep rock, including peridotite from near the Mantle. Nearby sit the St. Peter and St. Paul rocks, tiny islets made of that same deep material, pushed up to break the surface. The fracture zone is also seismically active, generating earthquakes as the plates grind along the fault. And yet, for all its importance, no crude submersible descent to the floor of the Romanche Trench has ever been recorded. It lies in a remote, empty stretch of equatorial ocean, far from any coastline, with little ship traffic passing over. Its depths have been mapped only coarsely, compared to the famous Pacific trenches. Deep currents scour its floor, sweeping away sediment and exposing bare rock. It connects vast basins, shapes the flow of the whole Atlantic, and remains, at its deepest, a place no person has ever been. Now, we turn to a sea everyone assumes we know by heart. Number 8, the Sigsbee Deep. Some unreached places are not exotic or distant at all. They sit just off a busy coast hidden beneath waters crossed by ships and oil rigs every single day. The Sigsbee Deep is the deepest point of the Gulf of Mexico, lying about 4,384 meters down in the southwestern part of the basin. People assume the Gulf is thoroughly explored. The truth is stranger. The deep is named after Charles Dwight Sigsbee, a United States Navy officer who, in the 1870s, made pioneering measurements of the Gulf aboard the survey ship Blake. He even invented an improved sounding machine that used wire instead of rope, finally making accurate deep soundings possible. The plain that surrounds the deep, the Sigsbee Abyssal Plain, is one of the flattest surfaces anywhere on Earth, built from countless tons of sediment carried in by the Mississippi River. Beneath that flat plain hides something restless. Rising up through it are the Sigsbee Knolls, dome-shaped hills pushed up by ancient salt buried far below. In 1968, the drillship Glomar Challenger sampled these knolls and found traces of petroleum, confirming that the deep Gulf was riddled with salt domes. That discovery helped make the Gulf one of the richest oil provinces in the world, with ultra-deepwater fields scattered across it. Here is this irony. Despite all that industrial activity, the actual deepest point has rarely, if ever, been visited by a crude submersible. The water there is cold, around 4 to 5 degrees, under roughly 430 times the surface pressure. The Gulf is a semi-enclosed sea, and its deep water renews only slowly, trickling in through the Yucatan Channel. The floor hosts cold seep communities, tube worms, and mussels and clams that feed on methane leaking from the seabed, and brine pools so salty and toxic that one has been nicknamed the Jacuzzi of Despair. The proximity to land gives a false sense of mastery. Hurricanes churn the Gulf's surface, but the abyssal Sigsbee Deep lies undisturbed far below. When the Deepwater Horizon disaster struck in 2010, it revealed how far industry now reaches into these depths, even as science lags behind. The sediments here quietly archive thousands of years of river flow and climate. A familiar sea, and still it hides a floor almost no one has touched. But not every unreachable place is defined by depth. Some would simply kill you. Number 9. The Cariaco Basin's Anoxic Depths. Off the northern coast of Venezuela lies a basin that is unreachable for a reason that has nothing to do with how deep it is. The Cariaco Basin drops to about 1,400 meters, which by ocean standards is modest. What makes it deadly is a shallow ridge, a sill only about 150 meters down that walls it off from the open Caribbean. Because deep water cannot flow in and out, the lower basin has gone completely without oxygen. Below roughly 250 to 300 meters, the Cariaco Basin is permanently anoxic. There is no dissolved oxygen at all. In its place, bacteria produce hydrogen sulfide, the gas that smells of rotten eggs and is acutely poisonous to almost all animal life. This makes Cariaco one of the largest permanently oxygen-dead marine basins in the world, and the most significant one in the Atlantic region. Below that boundary, no fish swim, no crabs crawl. Only specialized microbes survive. That lifelessness has a remarkable side effect. With no animals burrowing through the seabed to stir it up, the sediment settles in perfect fine layers, one for each year, called varves. This makes the floor of the Cariaco Basin one of the finest climate archives on the planet. Scientists can read those layers like tree rings, reconstructing rainfall, wind, and ocean conditions across thousands of years. Cores from here helped pin down ancient climate swings and even refine the calibration of radiocarbon dating. For more than 2 decades, from 1995 to around 2017, researchers ran the Cariaco Ocean Time series here, one of the longest continuous studies of its kind, led by Venezuelan and American institutions. They watched seasonal winds drive powerful upwelling, making the surface waters bloom with life even as the depths stayed dead. At the boundary between the two worlds, the chemocline, dense crowds of microbes perform exotic chemistry, building life from sulfur and carbon without any sunlight. No human has ever descended into that sulfidic deep. To enter it would be to swim into poison. Everything we know comes from instruments and sample bottles lowered from the surface. Cariaco is a living window into what Earth's oceans looked like in ancient times, before oxygen filled the seas, and a warning of what expanding dead zones could become as the climate warms. Some places keep us out by chemistry alone. The last place, though, is the largest of them all, and it is printed on every map. Number 10. The Global Mid-Ocean Ridge. The largest mountain range on Earth is one almost no human has ever seen. It is the Mid-Ocean Ridge, a continuous chain of volcanic mountains roughly 65,000 kilometers long, winding through every ocean basin on the planet. It dwarfs the Andes, the Rockies, and the Himalayas combined. And the overwhelming majority of it lies in cold darkness, 2 to 3 kilometers underwater, witnessed by no one. The ridge is where the planet builds itself. Along these seams, tectonic plates pull apart, and molten rock rises from below to harden into fresh seafloor. This is the engine of seafloor spreading, an idea championed by the geologist Harry Hess in the early 1960s and confirmed by Fred Vine and Drummond Matthews in 1963, who read the story in the magnetic stripes frozen into the rock. The ridge system includes the Mid-Atlantic Ridge, the East Pacific Rise, the ridges of the Indian Ocean, and the ultra-slow Gaukel Ridge buried beneath Arctic ice. Different parts grow at different speeds, from about 2 centimeters a year in the Atlantic to more than 15 centimeters a year in the eastern Pacific. The ridge rises 2 to 3 kilometers above the surrounding abyssal plains, and along its slow spreading sections runs a deep central rift valley. In just one place on Earth does this range climb above the waves. That place is Iceland, where you can actually walk along the ridge at Thingvellir. Almost everywhere else, it stays hidden. Only a tiny fraction of the global ridge has ever been surveyed in high detail, and even less has been seen directly by human eyes. This is where most of the planet's volcanism happens. Quietly, unwitnessed, producing around 75% of Earth's yearly output of lava along seams no one is watching. It was here, on the Galapagos Rift in 1977, that scientists in the submersible Alvin discovered hydrothermal vents and the astonishing communities of life around them, life that needs no sunlight at all. That single discovery rewrote biology, and it happened less than 50 years ago. The ridge is offset again and again by transform faults like the Romanche we visited earlier, and beneath the Arctic ice, the Gaukel Ridge remains one of the least explored places of all. We map this immense range mostly from satellites and ships, not from windows. The longest mountain chain on Earth, the birthplace of the seafloor itself, and still it is the least seen landscape on our planet. So after all our achievements, do these places stay beyond us? Across all 10 of these places, the same handful of barriers keeps returning. The first is pressure. For every 10 meters you descend, the weight of the water adds roughly 1 more atmosphere of force. At 5,000 meters, that is around 500 atmospheres, enough to crush ordinary equipment like a tin can. The second barrier is temperature, and it cuts both ways. The Arctic deeps sit near 0 degrees, the Beebe vents pour out water near 400 degrees, and a magma chamber glows at 900. No single machine is built to survive that whole range. The third barrier is chemistry. The Cariaco Basin would poison you with hydrogen sulfide. The supercritical fluid at Beebe would dissolve and cook an instrument at once. These places are lethal, no matter how clever your engineering. The fourth barrier is distance. Point Nemo and the Clarion-Clipperton zone demand days of sailing just to arrive, with no possibility of quick rescue, and wrapped around all of it is cost. A single borehole to the Mantle is estimated at around $1 billion, and even routine deep expeditions run into the tens of millions. This is why robots, not people, do most of the reaching. Autonomous and remotely operated vehicles go where no human body could. Yet even they fail. The Japanese robot Cariaco was lost in 2003, and the deep diving vehicle Nereus imploded in 2014 at nearly 10,000 meters. The deep does not forgive mistakes, whether the explorer is made of flesh or of titanium and steel. There is also the simple problem of mapping. Most of the seafloor has only been measured from satellites, at a resolution of about 1 kilometer, which means features the size of city blocks remain invisible. A global effort called Seabed 2030 is racing to map the entire ocean floor in detail by the end of this decade, but mapping a place from above is not the same as reaching it. And so the paradox we began with holds across every one of these places. We have walked on the moon, yet the largest part of our own world stays beyond our grasp, each location failing a different human limit. It would be easy to treat these places as curiosities, records to be checked off. But each one guards knowledge we genuinely need. Reaching the Mantle would finally settle what the moho truly is and reveal how deep life can survive inside a hot rock. Studying the seabed beneath Point Nemo would show us the absolute limits of life, surviving on almost no energy in the emptiest water on Earth, a baseline for what biology can endure. Entering, even remotely, the heart of a magma chamber would transform our ability to forecast eruptions, the kind that send tsunamis and ash across whole regions. The vents at Beebe carry clues to the origin of life itself, and to whether life might exist in the hidden oceans of Europa and Enceladus. The Molloy Deep holds the secret of how Arctic water sinks and drives the currents that govern our climate. Currents that may be weakening as the planet warms. The Clarion-Clipperton zone is a race against time. We are preparing to mine it before we have even cataloged the thousands of species that live there, and before we understand the strange claim of dark oxygen rising from its nodules. The Romanche Trench controls how heat moves through the Atlantic. The Sigsbee Deep preserves a year-by-year record of climate in its sediments. The Cariaco Basin is a living model of ancient oxygen-starved oceans and a preview of the dead zones that are spreading today. And the mid-ocean ridge holds the budget of the whole planet's volcanism, the factory where the seafloor is born. Run a thread through all of it and you find the same truth. Our ability to predict climate, to find new medicines from extremophile life, to understand the carbon cycle, and even to search for life beyond Earth, all depend on data locked inside places we cannot yet reach. Every unreached location is a missing chapter in the story of our own world. To send anything down at all, we rely on machines. Since human bodies cannot survive these places, we send proxies. The simplest are autonomous underwater vehicles, free-swimming robots like Autosub and Sentry, which roam the deep on their own and map the seabed in fine detail. Then, there are remotely operated vehicles tethered to a ship by a long cable, machines like Jason, HiBIS, and the Lost Cariaco, which carry cameras and robotic arms to grab samples. These are our hands and eyes in the abyss. A small number of crude submersibles still carry people down. The famous Alvin, recently upgraded to reach 6,500 meters, and the limiting factor, capable of reaching the very bottom of any ocean, have brought human observers face to face with the deep. For drilling, specialized ships like the Glomar Challenger, the Joides Resolution, and Japan's Chikyu bore into the seabed itself. And listening networks of underwater microphones, a legacy of Cold War submarine hunting, let us hear events we will never see. But every machine has its limits. Heat near magma and supercritical vents melts electronics. Ice over the Molloy and Gackle ridges blocks access and snags tethers. Pressure crushes hulls, as it did to Nereus at nearly 10,000 meters. Even when a robot survives, there is a lag in its commands and a limit to how much data its cable can carry back. A robot can bring home a sample, but it cannot bring home the experience of being there. New tools are emerging fast. Soft-bodied robots that flex under pressure, artificial intelligence that lets vehicles navigate alone, and swarms of cheap drones that could cover far more ground. Landers are dropped and left for months to record the deep in patience. Telepresence, with live video streamed from ships like the Nautilus and the Okeanos Explorer, now lets scientists on shore and the public alike watch discoveries unfold in real time. Each tool extends a different human limit, and together they are how we reach the unreachable at arm's length. So just how close are we, really? The honest answer is that we are closer than ever, and still far away. Between 2018 and 2019, the Five Deeps expedition managed something never done before, reaching the deepest point of all 5 oceans with a crewed submersible. The Molloy Deep, in the Arctic, was among the very last of those deepest points to be visited, only in 2019. The Challenger Deep has now been seen by a growing handful of people, yet still by far fewer than have traveled to space. Other frontiers are inching forward too. Plans to drill toward the Mantle continue, with Japan's Chikyu offering the closest thing to the right tool. Decisions about mining the Clarion-Clipperton zone are pending at the International Seabed Authority, and exploration there is accelerating. Follow-up studies are testing the startling dark oxygen claim. The Seabed 2030 project has already mapped more than a quarter of the ocean floor to modern standards and aims for all of it by the end of the decade. New nations are joining the deep. In 2020, China's submersible Fendouzhe carried a crew to the bottom of the Challenger Deep. Better materials, from titanium spheres to syntactic foam, keep pushing how deep humans can safely go. Fleets of cheaper autonomous vehicles are expanding coverage, and telepresence is lowering the cost of exploration year by year. The urgency of climate change is driving new monitoring of the Arctic and the deep ocean, but some of these places will likely stay robot-only forever. No human will ever sit inside a magma chamber, or in the supercritical heart of a vent, or in the poisoned deep of the Cariaco Basin. And the seabed beneath Point Nemo may simply never have a reason compelling enough to justify the journey. We are far better at mapping these places from a distance than at physically reaching them. The gap between knowing where something is and standing upon it remains wide, which leaves us with one last thought about the world beneath the waves. Look back across these 10 places and you see that unreachable means many different things. It can mean down, like the mantle beneath the crust. It can mean far, like the seabed under Point Nemo. It can mean hot, like Havre and Beebe, or cold, like the Molloy Deep. It can mean vast, like the Clarion-Clipperton zone and the endless mid-ocean ridge. It can mean poisoned, like Cariaco, or simply overlooked, like the deep floor of a sea we cross every day. Running through all of them is a single, humbling paradox. More people have orbited this planet and more have gazed at the moon up close than have ever reached most of these places in our own oceans. The sea covers roughly 71% of the Earth. The deep ocean is the largest living space on the planet, and yet we have sharper maps of Mars and the moon than we do of much of our own seafloor. Deep sea exploration is astonishingly young. The vents that rewrote our understanding of life were found less than 50 years ago. The deepest point of the Arctic was first reached only a few years ago. The blank spaces on the map are not relics of the past. They are still here, now, beneath the waves. And they shape our climate, hold unknown life, and may even hold clues to how life began. What we choose to reach and what we choose to exploit before we ever truly reach it is a decision being made in our lifetime. The last great frontier is not above us, scattered among the stars. It is below us, dark and patient and close. The map still has its blank spaces, and they are nearer than you think. The ocean, for now, is keeping its final secrets.